Well friends, myself Ashok Pooja, PGT Physics, JNV, Bangalore Rural. Today I am here to explain one of the important chapters in the 12th class physics syllabus, that is electromagnetic induction. You see, in the current electricity, we come across another phenomena which is magnetic effect of electric current. Now, what is the difference between these two phenomena? That is what we need to understand first. One is a magnetic effect of electric current, where a current flowing through a conductor produces a magnetic field, and other one is electromagnetic induction phenomena. You see friends, here the current is going to be the source of magnetic field, which was discovered by a scientist, Oersted, in the year 1820. When he discovered this phenomena, that time the question arises that whether the reverse of that, is it possible or not? That means when the current is producing a magnetic field, at the same time, is it possible for us to get the electric current from the magnetic field? This was the question. And this question was answered by another scientist, Michael Faraday, in the year 1831. A famous scientist who has discovered this electromagnetic induction phenomenon, Michael Faraday, he has shown that an electric current can be obtained with the help of a magnetic field. You see, if you look at the name of the chapter, Electromagnetic induction, which contains three terms in that. One is electric current, second one is a magnetic field, and third one is an induction. Now, out of three words, there are two forms of energy, and other one is a process. Then what are those two forms of energy? One is electric current and other one is a magnetic field. These are the two forms of energy. And what about the induction? Induction is a process actually, which can be carried out here. Okay, so from the name of the chapter itself, you can understand that a magnetic field can induce a current in a conductor. That means a magnetic field is capable of producing the electric current in a conductor through a process called induction. Okay friends, so this is what exactly meaning of this electromagnetic induction. In short, it is called as EMI. I will tell you friends, EMI is one in which one form of energy gets converted into another form of energy. Then what are those two forms of energies? Those two forms of energies are nothing but one is a mechanical energy and other one is a electric energy. So that means in this phenomenon, a mechanical energy gets converted into electrical energy. Well friends, as I was told, this phenomenon was discovered by a scientist Michael Faraday in the year 1831. In order to discover this phenomenon, Faraday has carried out two simple activities here. Using two materials, they are, one is a source of a magnetic field. It may be a magnet or it may be a current carrying conductor, because both of them produces a magnetic field. And the other one is a coil, which is made up of a good conductor of electricity, say a copper wire. Okay, when a copper wire is wound, it can be wound in the form of a coil which contains number of turns and all that. Right? And you see, now I try to explain two simple activities carried out by a Faraday in order to discover this EMI phenomenon. Right? And here you are seeing two materials. One is a coil made up of a good conductor of electricity, and other is a source of magnetic field, that's a bulk magnet. Okay, now both the materials are at rest position. Even though something is there, when both the materials are placed very near to each other, something is there. So what is that? That we say that a magnetic flux linked with a coil. That means whenever we are placing a magnet near a coil, so many number of magnetic field lines are in touch with a coil. And that situation, we call it as a magnetic flux linked with a coil. But actually, the Faraday has shown that whenever there is a change in the magnetic flux linked with a coil, an induced EMF is produced across the two ends of a coil when the coil is open. On the other hand, when the coil is closed, an induced current directly begins to flow through a coil there. Okay, now ultimately the question arises that how to change the magnetic flux linked with a coil here? It is very simple. If at all you want to change the magnetic flux linked with a coil, you need to have a relative motion between the two materials here. When the coil is at rest motion, move the magnet in and out. On the other hand, keep the magnet at rest motion and move the coil in and out. In both the situations, there exists a relative motion between the two materials. And because of the relative motion, the magnetic flux linked to the coil ultimately changes. And accordingly, EMI phenomena, an induced EMF exists between the two ends of the coil when the coil is open. On the other hand, if the coil is closed and directly the induced current begins to flow through it. Okay, so this was the simple activity carried by Michael Faraday to discover this phenomenon. And accordingly, what happens here? Whenever there is a change in the magnetic flux linked to the coil, an induced current flows through a coil. Okay, this is one experiment. And other experiment you see, this is what this is the second experiment where he has used two coils. Okay, this is the first coil and this one is the second coil. Now across the two ends of the coil, you can see a source of energy. Say there's a battery which is connected between the two ends of a first coil here. And of course, there's a tapping key. Okay, and near to this, one more coil is placed where the two ends of the coil are connected to a galvanometer. Right? When this tapping key is kept open, the point of a galvanometer doesn't show any deflection. That indicates that there is no flow of current in the secondary coil. On the other hand, when you press or release the tapping key, then what happens? The magnetic flux linked to the secondary coil changes. And according to EMI phenomena, the points of a galvanometer shows a deflection. That indicates that there is a flow of induced current in the coil. So these are the two simple activities carried out by Faraday in order to discover the phenomena electromagnetic induction. Okay, and during his carrying out of these activities, he made so many important observations in connection with the magnitude of the induced EMF and all those things. And whatever the important observation that he has made, that he has kept it in the form of a law. And that we are learning it as Faraday's law of electromagnetic induction. And this Faraday's law of electromagnetic induction always gives the magnitude of the induced EMF, magnitude of the induced voltage. If you know the resistance of a coil, then you can easily calculate the magnitude of an induced current. So therefore, the magnitude of the induced EMF or the magnitude of the induced current was given by Faraday, according to this law. What the law says, Faraday's law, it says that the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux. So therefore, what I mean to say is that the induced EMF in a coil increases with increase in the change of magnetic flux with respect to the time. When the rate of change of magnetic flux, starts increasing, then what happens? The magnitude of the induced EMF also increases, and vice versa. If the rate of change of magnetic flux is very less, ultimately a lesser value of induced EMF or the induced current, produces in a coil. That means how fast we are moving, a magnet towards a coil, that counts a lot. How fast the current increases in a coil, how fast the current decreases in a coil. Okay, here also, how fast you are moving the magnet in and out. Okay, so that comes a lot here. So that means the rate of change of magnetic flux decides the magnitude of a induced EMF. Right? So as I told, the magnitude of the induced EMF is given by Faraday's law. Whereas the dash of the induced EMF or the dash of the induced current was given by another scientist, that's by the Lenz, that we learned it as a Lenz law. So the Lenz law, it gives the dash of the induced EMF or the dash of induced current in a conductor. And according to Lenz law, what it says, the induced current in a coil flows in such a way that it always opposes the cause. It always opposes the cause. So that means here, whatever the cause which produces the induced current, it always gets opposed by the induced current, that is flowing in a conductor and all that. In that direction, the current flows. The induced current flows in such a way that it always opposes the cause that it has produced. Okay? In the first case, what is the cause? What is the cause of the induced current here? The cause of the induced current, motion of a magnet towards a stationary coil, or motion of a coil towards a stationary magnet. And here, what is the cause? Here, the change of current is the cause. The current may be increased, the current may be decreased. These are the cause. So these things will be always opposed by this induced current. So that means this induced current always has what? Negativity, negative in nature always, which always opposes the cause that it has produced. Say for example, you see now, when this north pole of a magnet is moving towards a stationary coil, definitely due to that EMI, induced current flows in a coil. It flows in such a way that it always opposes the cause. That means we know very well that whenever the current is flowing through a circular loop behaves like a magnet dipole. On one pole, on one place, if north pole is created, on the other place, a south pole will be created. Okay, that's what. Of course, what kind of pole is going to be produced on a particular face of a coil can be identified by the N rule. Right? Now here, as such, when this north pole is moving towards a stationary loop, the current induced current flows in the coil in such a way that on this face, always there should be a production of a north pole, so that there will be a repulsion. Okay, so because of the repulsion, opposition will be there. In order to keep this magnet to move further, an external agent has to do a work. Okay, so that means when you are moving a magnet towards a stationary coil is nothing but a mechanical work, mechanical energy. And that mechanical energy gets converted into electric energy here. So that means here, what is going to happen now? The current flows in the, in such a way that which flows in the anti-clockwise direction. So that on this space, a north pole is going to be created. So this Lenz rule is one rule with which you can identify the dash of the induced current. And one more rule is also there to identify the dash of the induced current. That we call as a Fleming's right hand rule. This is what the Fleming's right hand rule. According to that Fleming's right hand rule, when you are holding the thumb, forefinger and the middle finger of a right hand mutually perpendicular to each other, this forefinger always gives the dash of the magnetic field. Okay? And this thumb gives the dash of the motion of a conductor in a magnetic field. And whereas this middle finger gives the dash of the induced current in a conductor. Okay, even you can use even the Fleming's right hand rule also to identify the dash of a induced current in a conductor. Well, friends, in order to teach the chapter electromagnetic induction more effectively in the classroom teaching and learning process, I have made my own model based on this EMI phenomena, and the name of that model is what I call it as a induction coil. So this is my model with which I can teach EMI concept more effectively here. Not only the EMI concept, apart from that, I can show a changing magnetic field produced by this model, and also eddy currents that I can teach very effectively, mutual induction phenomena. In addition to that, I can also teach a step-down transformer. So it is a single model with which I can teach many concepts while introducing the chapter EMI. If that is the case, friends, let us try to understand what are the important parts of this induction coil. Okay, and this is what my model, friends. Here is a half meter length PVC pipe in which I have placed nearly 40 number of iron rods, because these are the iron rods which are basically ferromagnetic material which are highly useful to link the flux. And here is a big bobbin which is containing nearly more than 1000 turns of the insulated copper wire, whose two ends are connected to a 2-pin plug. Okay, a 2-pin plug, and with which I can pass an alternating current. Here you can pass an alternating current because this coil can withstand that current, because the length of the coil is very more here actually. So that's why this coil is capable of withstanding an AC current here, right? And I have made my own stand in order to place this coil vertically. Okay, and also I have made my own AC source arrangement here. An AC source socket is also there, where using this AC source socket I can pass alternating current through that coil. Right? Well, friends, this is what my MOI, the coil which I call it as a induction coil, and I can place it like this here. Alright, it can stand firmly, vertical, right? And now I can pass a AC current through the coil. Right? When I switch on the circuit here, well, friends, the current begins to flow through a coil. And we know very well that whenever the current flowing through a conductor, around that a magnetic field will be there. Okay, since the type of the current that's flowing in a coil is AC current, an alternating current. An alternating current is one which always reverses its direction, changes the magnitude continuously. Since there is a flow of AC current, so therefore around that there is a changing magnetic field. Right now it has produced a changing magnetic field. Now let us test that whether there is a changing magnetic field or not. For which I am using a small disc magnet. I am using a small disc magnet here, which is having poles on both the faces. On one side, if there is a north pole, and the other side, there will be a south pole. And just I place this disc magnet, a small disc magnet, in a container like this, and then I hold it here. See, there is a vibration in the magnet. The magnet is vibrating. See, everywhere the magnet is vibrating. See, there is a changing magnet field everywhere. Okay, friends, see that? Now the question arises that why does the magnet vibrates here? It is very simple. Now there is a changing magnetic field. That means whatever the coil that I have used here, it acts as a solenoid, and current carrying solenoid is equivalent to bar magnet only. But here what is happening, because of the flow of AC current, the polarities on the ends of that solenoid keeps on changing. Momentarily the north pole is produced, means other side south pole will be produced, and next moment the south pole will be produced here and north pole produced at the down place. And because of that attraction, repulsion, this magnet is keep on vibrating here. So that indicates that there is a changing magnetic field, right? So right now I have a changing magnetic field here. And Faraday has shown that whenever a conductor is placed in a changing magnetic field, an induced current begins to flow through a conductor. Okay, if the coil is closed. If the coil is open, then induced EMF is produced across the two ends of a coil. So for which, what I did here, I have taken, so it is a small bobbin which contains 30 turns of insulated copper wire, whose two ends are connected to a torch bulb. Here is a torch bulb, right? Now here I have a changing magnetic field, and here is a conductor. According to electromagnetic induction phenomena, when the conductor is placed in a changing magnetic field, the magnetic flux linked to the coil changes. And according to EMI, an induced current begins to flow through a coil. As a result of that, glow. That's what you can find here. Come on, friends. See there? The bulb is in glow now. It is glowing. Because what is happening here? The magnetic flux linked to the secondary coil is changing. And according to EMI, you see, the induced current is flowing there. And hence, the bulb is glowing. Right? This is what a simple phenomenon of electromagnetic induction is. You see now, when I take this coil away from the primary coil, the brightness of the glow is decreasing. On the other hand, when I take the same secondary coil near to the primary coil, the brightness of the glow is increasing. You see, just recall your memory regarding the Faraday's law. What it says, the magnitude of the induced EMF and hence the induced current is always directly proportional to a rate of change of magnetic flux linked in the coil. Okay, actually, near this point, near the primary coil, the magnetic field is very much stronger. As one goes away from the coil, the strength of the magnetic field decreases, and hence the rate of change of magnetic flux also decreases, and accordingly there is a decrease in the glow of the bulb. Okay, so this is what a simple phenomenon of electromagnetic induction. That means a changing magnetic field is inducing a current in a coil, and accordingly the bulb is glowing there. Right? Okay, friends. This is what. Okay, stop. Well, friends, just now we have seen that when a conductor is placed in a changing magnetic field, according to EMI, an induced current flow through a conductor. Now, instead of placing a conductor, if you place a conducting plate in a changing magnetic field, what may happen? That's what my next doubt. And let us verify what's going to happen. Okay, now here is a conducting plate. It is a conducting plate actually, which is made up of a aluminum material. Right? Now what I do here, I just switch off the circuit. Okay, and I place the conducting plate here. Right? Okay. Now let me switch on the current. What may happen? To your surprise, you see, the plate is jumping. The moment when I switch on the current, the plate jumps up into the air. Why? What may be the reason here? Friends, I'll tell you. Instead of conductor, we have placed a conducting plate. Now, in the conducting plate, according to EMI, so many number of closed currents which are also induced current. And these closed induced currents which are flowing in a conducting plate are said to be eddy currents. So right now, eddy currents are produced in a conducting plate. And you know very well that the induced current always opposes the cause. And it is because of that, what happens here, the moment when I switch on, momentarily on the upper face of this coil, if north pole is created, means on the lower face of a conducting plate also a north pole will be created. And we know very well that the like poles always repel each other, and it is because of this reason a conducting plate is jumping. And also you can say that now anyway here the conducting plate is also placed in a changing magnetic field. Even the conducting plate also gets magnetized, and it is because of that the conducting plate is jumping. Okay, so this is all because of the production of the eddy currents in a conducting plate. Now you see here, friends, what I do here, I don't allow the plate to jump. Okay, I don't allow the plate to jump. I'm just holding it. Okay, if you hold it, then what is the experience that you are going to have here? I can experience heat energy is being produced here. The plate is very hot. Why? Because the amount of energy with which it is supposed to jump that gets converted into heat energy here. And this is the phenomenon. This is a simple process which is being used in an induction stove. You see, since the conducting plate that I am using here is very light plate, so that's why it is jumping. Now instead of using a lightweight plate, if you use a heavy plate, then what happens? So because of the heavier mass, the conducting plate never jumps. Rather, we get a sufficient amount of heat energy from that. And that heat energy can be used for cooking purposes. So therefore, whatever the eddy currents which are being formed here now, these are the eddy currents can be used in order to heat up the materials and all that. And this is the simple working principle of an induction stove. So this is what ultimately the induction stove is going to have this eddy currents as the working principle here, friends. See? So beautiful it is. So nice it is. So nice. Yeah, it's all because of the eddy currents. Well friends, this model can also be used for explaining the mutual induction phenomenon. According to mutual induction phenomenon, it is a phenomenon according to which an opposing induced current is flowing in one coil whenever there is a change of flow of current or the change of magnetic field in the neighboring coil. Okay, you see now, right now I have two coils here, and this is what I call it as a primary coil through which an alternating current is flowing. So that means AC current is flowing there, which continuously changes with the time. So because of the flow of changing current, around that there is a changing magnetic field, and that changing magnetic field through these ferromagnetic materials gets linked with a secondary coil. Now this is the secondary coil and this is a primary coil, right? See, you just recall your memory. Mutual induction phenomenon, what it says, whenever there is a change of flow of current or change of magnetic field in one coil, which always induces an opposing induced EMF in the neighboring coil. This is what we can see here. This is what you can experience a mutual induction phenomenon. This is nothing but a mutual induction phenomenon. And this mutual induction phenomenon serves as the working principle of a transformer, which is used to change the voltage, AC voltage, from one value to the other value. Right now, here you are seeing actually, and this is nothing but a step down transformer only. Here I have applied an AC of 220 volt. Okay. An AC of 220 volt across the primary coil, and across the secondary coil, how much voltage that I am getting here? Hardly 2 or 3 voltage that I am getting here in order to light the bulb here. Okay, so that means here the AC voltage has been changed from the higher value to a lower value. So therefore, this model itself is going to act as a step down transformer here, and this is nothing but a mutual induction phenomenon. There is a production of opposing induced EMF in one coil due to the flow of changing current or changing magnetic field around the another coil. Well friends, here is a simple activity to demonstrate EMI phenomenon. Here I have two things. One is a coil, insulated copper wire wound on a PVC pipe, whose two ends are connected to the two terminals of a galvanometer, which always identifies the flow of a small amount of current in a coil. And these are the magnets which can produce a magnetic field around it. Okay. Now what I do here, I just place the magnet inside a PVC pipe. When I place the magnet inside a PVC pipe, there is no flow of current in a conductor because there is no deflection in the point of a galvanometer. It's all because both the things are at rest position here. Coil and the source of magnetic field, both of them are at rest position. But there is a magnetic flux linked with the coil. And as per EMI phenomenon, an induced current flows through a coil only when there is a change in the magnetic field, magnetic flux linked to the coil. And the magnetic flux linked to the coil can be changed by having this relative motion between the two metals here. Now, when I move the magnet in and out you can see there is a deflection in the pointer of a galvanometer. That indicates that there is a flow of induced current. But the pointer of a galvanometer is deflecting on both the sides of a zero reading there. That indicates that the direction of the flow of current is reversing just by reversing the motion of a magnet here. When I move the magnet outward, the current flows in one direction. On the other hand, when I move the magnet inward, the current flows in the other direction. So that means by reversing the motion of a magnet, we can reverse the direction of the flow of current. So this is the simple activity to explain this EMI phenomenon. Yes. Well friends, so far we have learned something about electromagnetic induction phenomena. Okay. Is there any application part of this EMI? Yes. This EMI phenomenon is going to serve as the working principle of our very, very important device is none other than generator. Okay, a generator is a device which converts the mechanical energy into electrical energy. Okay, and here is a simple model of a generator in which we can show the mechanical energy can be converted into electrical energy. Okay, so this is what the generator or right. When I rotate the handle here, then what happens, the light begins to flow. So this is how the dynamo or the generator works. So dynamo or generator is a device in which the mechanical energy gets converted into electrical energy. And this is a simple application of electromagnetic induction phenomenon. That means here in this device, inside this device, the magnetic field is kept constant, whereas coil, which is there in the form of armature, starts rotating there. When the armature starts rotating, the magnetic flux linked to the coil changes and accordingly the current begins to flow in a coil and hence the bulb glows here. Okay, thank you friends. Thank you.